Welcome to this introduction to electronics tools. This semester you'll be doing a lot of electronics-based labs, so before we can get to those, we need to explain how to use the tools effectively and safely so that you can get the most out of your lab experience. Before we begin, let's just cover some basic circuit concepts. And you'll go more in depth later during the semester, but for now, let's just cover some fundamentals. So at its simplest, a circuit is just a bunch of components connected together in a complete loop that allows the current to flow through them, and it does different things when it passes through each component. So we might have some sort of power source here, and then some components here, which I can represent generically at the moment as boxes. And if we were using specific components, then we would replace those boxes with the circuit symbols for each one of those. And if we complete the circuit and bring it back all the way around so that it forms a complete loop, this will allow the current to flow through the whole thing in a loop, which we can represent the current as the variable I. Now the next thing to distinguish here is the difference between series and parallel circuits. So a series circuit is really just what it sounds like. It's a bunch of components connected together in series or in sequence so that the current just flows from one to the next to the next to the next. So we can draw this here. We'll have one component, another component, and another component, and we'll just connect them one to the other and then back around and form a complete loop. And instead of a complete loop, you could have this connected to other stuff in your circuit, but these three components are now connected in series. Now parallel, when we think of parallel normally, that would be like maybe parallel lines, and it's really the same idea when we have a circuit. So we might draw again our three components, and then instead of connecting them in series, one to the other, we're going to connect them in parallel. So if you just think about it here, we've got now parallel lines going through each one, and then we connect them top and bottom, so now each one is in parallel to each other. And that's all we mean by parallel. The next thing we need to cover is the multimeter in your lab kit. And I have two different models here. These are not the ones that you'll have in your lab kits, but these still do the same sort of things, so we can explain the concepts with these. The basic function of a multimeter is it measures things in your circuit, so that would be your voltage, current, and resistance. And some multimeters do measure other quantities, but for these labs, you're only going to be looking at those three values. So the first thing to notice about these is we've got these red and black probes. And really the color doesn't matter, but by convention, the black one is your negative lead, and your red one is the positive lead. And here at the bottom of the multimeter, you'll see that there are some different ports where you can plug them in. And depending on what you want to measure, you'll use different ports for different things. The black one is always going to go into the common port. So that one always goes there. And then for voltage, you'll find the one where it says V for voltage. And then if you want current or resistance, then you just find the appropriate port for that. So for now, I'm just going to plug it back in to voltage. The next thing to notice is the mode dial, which you can turn to the different function that you want to measure. So the first one here on mine is voltage, and you can see that we've got two different voltages here. We've got V here with a little wavy line on top, and then V with a solid and dashed line on top. And whenever you're talking about circuits like this, the wavy line is alternating current, and the dashed line with the solid line, or even just a solid line, is your direct current. So for these labs, we're just going to be looking at direct current, so I'm just going to turn it to that. And again, you want to make sure that you have your common one with the black, and then the voltage with the red. So then all you have to do is just press your probes against that, and then you touch them to the two leads where you want to measure voltage, and then you get your value from that. So right now, if these are connected together, we have 0 volts because there's a 0 volt difference between these two probes. There's no voltage source connected. For multimeters, you're going to either have manual ranging or auto ranging, and auto ranging just means that it can automatically detect what range of values to measure for, and manual ranging means you have to set it to the correct range of values for measuring. For the one I have here, it looks like it's mostly auto ranging, although there are two categories here for voltage. We've either got just regular volts, or we've got millivolts. And millivolts, that's just 1,000 times less than a volt. So if I'm going to be measuring very small voltages, then I would want to set it to the millivolt rating. And if I want to measure larger voltages, then I would set it to the volt rating. And for other ones where they have more options, then instead of just having like 2 settings here for volts and millivolts, they might have up to 2 volts, or up to 20 volts, up to 150 volts, or whatever. So let's say that you wanted to measure something that was 5 volts. Well, then you couldn't do the 2 volt rating because that's too low. It wouldn't go up high enough. So then you'd have to go up to the next one up, which maybe would be 20 volts. So that would just mean you could go up to 20 volts, but you don't have to go up that high. So if you have 5 volts, that would fall within the range of 2 volts to 20 volts, and then that one would be the correct setting to use to measure that. As I mentioned earlier, the different components in our circuit are going to be represented by different circuit symbols. So for a voltmeter, which is what we measured here, then the symbol is going to be something like this, where we'll have a circle with a V through it. So if you see that, that just means you're going to have a voltmeter in your circuit. The next thing to look at is going to be current. So for mine, I can turn this over here to current, and since current is measured in units of amps, then the A symbol here, or milliamps or microamps, are going to be the settings that you want to look for measuring current. And again, we want to make sure that the red probe is on the correct port. So right now, I want to unplug that. See, this one doesn't have current on here. So if I wanted to measure small currents, meaning milliamps or microamps, then I could plug this one in here, and then that would allow me to measure milliamps or microamps. And if I wanted to measure larger currents, then I can move this over here, plug it into the 20 amp port, and then turn this over to amps. And depending on what your multimeter has, these ranges are not going to be the same. They may be numeric ranges where maybe it's 0 to 500 milliamps or up to 2 amps or whatever, but just select the correct range on the dial and then put your probe in the correct port. So for most of the things that we're going to be doing, you'll be wanting to have it on the lower current rating, but just double check and see, if you're expecting something higher than what it can handle, then you definitely want to put it on the higher rating and select that on the mode dial. So something that is very important when you're measuring current with a multimeter is always connect it in series. So we talked about the difference between series and parallel circuits. So series, again, just put it in sequence with the things that you want to measure the current flowing through. And if you don't do that, if you connect it in parallel, it's going to act like a short circuit that will connect between those 2 points. All the current is going to flow through there. It'll be a large amount of current with very little resistance, and you'll burn out the fuses on your multimeter or even destroy it, and it will stop working. And I did that with this multimeter. I don't know when. It just doesn't work now. So if I leave it here on the lower current rating and I try to measure current, I don't get any value from that. So please keep that in mind. If you don't want to destroy your multimeter and not be able to do the labs, then make sure that you always connect it in series and connect it on the right port depending on the range of values that you're going to be using, so that you don't burn out your fuse or destroy your multimeter and make it no longer usable. Again, when we're talking about circuit symbols, there will be different symbols depending on what we have in the circuit, what the component is. For measuring current, we would call that an ammeter because it's measuring amps. And so we just write here ammeter and represent it by a circle with an A through it. So if you see that in your circuit, then that just means that you're measuring current at that point. The next thing we can measure here is resistance, and that is represented by the Greek letter omega. And omega just stands for ohms, which is the unit for resistance. And again, you want to switch your multimeter probe to the correct port, so don't leave it on current. Put it back here to where it says ohms, and you can see the Greek letter omega here as well. That will be for measuring resistance. If your multimeter is not auto-ranging like this, I only have one setting for measuring resistance, then you would just select the appropriate range. If you're measuring, say, 500 ohms, then you wouldn't want to set it on the 200 ohm range. You'd maybe want to set it on the 2 kilo ohm range or something like that. So just make sure you select the appropriate range. Always go as small as you can with the range so that it has the highest precision. But if you have it too far, then it's not going to show up with anything. you'll notice right now that the screen says OL, and that would stand for open loop, meaning there is no connection between the two probes. Depending on what your multimeter is, it'll show something different there. If you don't have anything connected across it, it might show a 1, meaning it reached the maximum, it can't display anything else, or it might have something else there. But if it shows something like this, then that just means you've exceeded the maximum for that range. In my case, it's an infinite resistance. There's nothing, connected across here. But if I connect them to each other, then you'll see it drop very quickly back to 0, or in this case, very close to 0. So there might be a small amount of resistance in the probe wires, but it's essentially back to 0. So if I connected this to something else, then it would show the resistance for that instead. The last thing to note about measuring resistance is the circuit symbol. So when we're measuring resistance, we call it an ohm meter. And so then we just put the symbol for ohms, the omega, inside a circle again, just like we had A and V for amps and volts. The other thing we can measure here is continuity. And for mine, continuity is this little buzzer symbol. So it kind of looks like maybe some sound waves propagating out from a point source. For yours, it may not be on the same setting as resistance, but that's where it is with mine. All I have to do to change that is just press the select button, and now up here it shows that it's on continuity. And continuity just means that if you connect the two probes, then a buzzer will sound to alert you that connection was made, continuity was made between these 2 points, which just means the resistance was very low. So if I connect these right now, it beeps at me, just letting me know that that was connected. This is very useful to use when you're trying to debug your circuit. If you're not sure if something is working or not, then just use your continuity probes, touch it here, touch it there, and see if it was supposed to have a connection between there and it doesn't, then something's wrong. But if it does beep, then you're good. That may not be where the problem is. You just move on to the next part. So this is a really useful tool when you're trying to debug a circuit and make sure that it's working, which you're likely to encounter at some point, so just keep that in mind. The last thing to notice with the multimeter is the hold button. And all that does is it just grabs the value that you currently have on the screen, and it freezes it there so that if you stop measuring it, then it still stays there. So let's say that I'm measuring resistance again, I touch these across each other, and I get some value here. Rather than continuing to hold that on there, I can just press the hold button, and now I can separate these and the value stays there. And if I let go of it, if I press it again, then it just goes back to the live value. But here again, if I touch this, press hold, looks like I grabbed it while it was still ranging down, so that's not an accurate value, but I could hold this on here again, wait for it to reach 0, wait for it to equalize. If it was a different value, it wouldn't be reaching 0, but it reaches its final value, you press hold, then you can set the probes down, record your value, and you don't have to worry about holding your probes on the circuit and recording the value at the same time. So that's just a useful tool when you're trying to write down values or see it and it's changing a lot, so just press hold. Next up is the breadboard. And the basic function for a breadboard is just it allows you to make a circuit quickly and without making permanent connections. So rather than having to solder things onto a circuit board, you can just plug them into the different holes on here and make the connections quickly and easily. The breadboard that I have here actually has 2 breadboards on it, so it has a panel here on the right and a panel on the left. The one that you'll have will just have one of them, so that would be just like from here to here, going up like that. So just this portion. Now there's often a lot of confusion about how these breadboards are wired up, but it's actually fairly simple. You just need to understand the 2 main areas that we have, which are the power rails and then the rows. So for each breadboard we have 2 power rails. We have the red and blue line on this side and then the red and blue line on this side. And in my case I've got double that, but for you, you would just have the red and blue lines here and then the red and blue lines here. And then in the middle are the rows. So the entire blue line, which is this first row of holes, that's connected underneath all the way down. So if I connect something here on the blue line all the way up to here on the blue line, those 2 holes are connected, or these 2 holes, or these 2 holes. So all holes in that row, or rather that column, are connected together, and the same with the red. So on the right row, we've got all the red here, and those are connected. But this entire power rail section here. So just this row here is not connected to anything else. So it's separate, but all the holes on the blue row are connected, all the holes on the red row are connected. And it's the same thing over here. All the blue holes here are connected to all the blue holes here, and the same with the red. But these power rails are not connected to these power rails. So these two are separate from each other, but all the blue holes in this column are connected to each other, all the red holes connected to each other, and the same over here. For the rows, we've got two different halves of that. So we've got this section of rows and then this section of rows. So for each row, you have like row 1, these are numbered on here, row 1, 2, 3, 4, 5, and so on. So everything in a row is connected together. So everything in row 1, there's 5 holes there, those are connected together. And then on this side, row 1, all of these holes are connected together. And it's the same with row 2. All the holes in row 2 on this side are connected, all the holes in row 2 on this side are connected, and so on and so forth, going all the way down. So let me briefly try to draw out how this is laid out. So we have the power rails, which are just basically lines underneath. So we've got the blue lines and the red lines. And then we've got the rows. So we would have row 1, row 2, 3, 4, so on, going all the way down to the bottom rows. And then we have the same thing reflected on this side, where we'd have this row, this row, this row, this row, going all the way down to the bottom, where we've got those rows. And then again, we've got the power rails on the other side, where we've got the red and blue lines there. So if we compare that now to this, where we have the two power rails, we've got blue and red, and the same over here, blue and red, and then we've got rows, 1, 2, 3, 4, so on, going all the way down to, looks like 61, 62, 63. And again, everything, all the holes on this row are connected, so we'd have our little holes going down like that. And then the same thing here, 1, 2, 3, 4, 5 holes in a row. Same on this side, 1, 2, 3, 4, 5. And, same over here on this power rail. But everything in this line is connected together, everything in this line is connected, each row is connected to each other like that, but not through the middle. So if you wanted to connect something, from this side over to this side, then you'd have to put a wire that would go, from this hole over to this hole. So that's how a breadboard is laid out. The main thing is the power rails. You've got blue line, red line, everything in blue is connected, everything in red is connected, and then the rows, you've got 1, 2, 3, so on, and then the same on this side, 1, 2, 3, and so on. Next up is the battery, and this is something everyone is more or less familiar with. We've all used batteries before, and I've got a 9-volt here, which has the positive and the negative parts to it. So then I have a battery connector here, which we can snap on with the correct polarity. And the connector I have here has a barrel connector on it, which doesn't work for the breadboard, so I have an adapter. The ones that you'll have for your lab kits will already be bare wire, so you can just plug it on to the battery and then plug the other ends directly into the breadboard. So this is just an adapter, but red line to red line and black line to black line. The circuit symbol for a battery is going to look like this, where we have a long line, then a short line, another long line, and a short line, and then your circuit would come out of those, where this is the positive side and that is the negative. And then you can put the voltage out here, so if it was a 9-volt, then you would write 9V here, or if you wanted to name it, if it was V source or something like that, then you could write that next to it, but this is the symbol then for a battery. The next component is the capacitor, and the basic function of these are just to store charge, which if you measured it across the two leads, you would find a difference in voltage. The capacitors that you have are polarized capacitors, meaning there's a positive lead and a negative lead. The way you can tell which one is which is the positive lead is going to be longer than the negative lead. The capacitor I have here has already been trimmed short, so I can't show you the difference in lengths of the lead. But the other way you can tell is look at the side of it and you'll see the strip where it's got maybe negatives written on it or maybe zeros or something like that. And that one is going to be the negative lead. So again, the positive lead is the long lead and then the negative lead is the one that has the strip, and it's the short lead. The unit for capacitance is the farad, represented by F. So if you look right here on your capacitor, you'll see that it says 1000 microfarads. Microfarads is mu F, the Greek letter mu, and then F. So that's 1000 microfarads. But that is the nominal value, meaning 1000 microfarads is what it's supposed to be. In reality, it's going to probably be off from that a little bit, some percentage, maybe 5, 10, 20%, whatever, depending on the capacitor. So you won't actually be able to check that with your multimeter because multimeters, the basic multimeters can't measure capacitance, but just be aware that the nominal capacitance is what's written on the capacitor, but the actual value is going to be different than that by some small percentage. The circuit symbol for your capacitor is going to look something like one of these, depending on what the capacitor is. For non-polarized capacitors, it's going to look like this one, where you have just the two lines here representing the two parts of your capacitor, the two sides, positive and negative. But for non-polarized, it's not going to matter which way you have it installed, so this is just going to represent, it could be positive on this side and negative on that side, or the other way around, positive on top, negative here. For polarized capacitors, you would normally want to do it something like this, where you can at least put a plus on one side to represent that that's the positive lead. And the other way you can do it is have this curved line, which represents the negative side. And so either one of these is good for polarized capacitors. If you want to do the other way, that's probably also fine. Some people would argue that you should always do something like this if you're dealing with polarized capacitors, but as long as you're aware of what your circuit is representing, and maybe if you add a little plus to show that this side is positive, the other side is negative, then you should be good with that. Next up is the resistor. And a resistor is just a circuit component that resists the flow of current, just like its name says. And the unit for a resistor is ohms. And ohms is represented by the omega symbol, as I mentioned earlier with the multimeter. If you look at a resistor, you'll see that it has some different colors on it, these different color bands, and those are the way that they specify what the value of that resistor is. If you want, you could look up the code. Each color represents a different value or a multiplier, and then the last one represents the precision, or how accurate the resistor is. The other way you can do it is just to use an app like this, where if I look at this resistor, then it looks like I've got yellow, purple, and brown maybe. So let's try that. So we have yellow, purple, and then brown. So that would be a 470 ohm resistor based on those colors, and the last color is gold. So that would, okay, that's already set. So that would be plus or minus 5%. So the value for this resistor is going to be 470 ohms plus or minus 5%. So this one was a 4-color resistor code, but they also make 5-color codes. And if I switch over to that, then you can see here we've got green, and then brown, black, and then brown again. And this one has brown for the precision. So this resistor then would be 5.1 kilo ohms, and the precision is plus or minus 1%. So whatever the resistor you have, you can either look this up in a table, or you can look it up with an app or something like that. So just use that when you want to know what the values are, or measure it directly with your multimeter. The circuit symbol for a resistor looks something like this, where you've got a zigzag line. And then for the value, you would put that next to it. So if this was 5.1 kilo ohms, then I would write 5.1 and then K omega for ohms. For this next part, we're going to try some stuff hands-on, and I want you to follow along with me and try this yourself. So first of all, let's measure the resistance of some resistors. So I want you to find the 470 ohm resistor and the 5.1 kilo ohm resistor. And you should have those in your lab kit, and if you don't, then you can find some other values that you could use instead. First of all, we need to measure the resistance, so we'll use the multimeter and switch that to resistance. And then to measure something with the multimeter probes, what you want to do is just place them down into the little breadboard holes. So first of all, put your resistors into the holes, both ends of the resistor, and then you can press the probes down into the holes like that, and it'll kind of hold itself in place. You know, it won't wiggle around. You can kind of get it fixed there in position. So just checking this right now, this one says that it's 5.077 kiloohms, which is very close to the nominal 5.1 kiloohms. And if we checked this other one here, where it's supposed to be 470, we have 463.34 ohms, so that's very close to this 470 ohms, which we predicted. Now that you've tried that, let's go ahead and build a simple circuit with a battery and a resistor. So we'll put the battery in place here. Just put the black lead in and the red lead. And just so you can practice using the power rail, let's put it in on that. So put the black one on the blue line and put the red one on the red line. I'm going to do it at this end. It doesn't matter which end you put your wires in at, but both of them will work. Sometimes if the wires are a little bit too flexible, then they won't go in very well, so you may just have to pull it back out, straighten the wire, and then try again. So now that's in, and we have power, and we can double check this if we switch it to voltage. And I'll just put the probes against here, and you'll see right now it's a negative 8.66 volts, and that's just because I accidentally switched them and put the black lead on the red one and the red on the black, so it was measuring it backwards. If I switch it now, you'll see that it's a positive 8.66 volts. Okay, now let's put our resistor in. I'm just going to set the 5.1 kilo ohm one to the side, and let's just put our resistor in here from there to there. Doesn't really matter where you put it, as long as the two ends are in different rows. Alright, so just grab some wires here from your jumper wire kit and find some appropriately sized wires so that you can go from the power rail over to the resistor. So I want to have the black one going to the bottom here. Could be to the top, it doesn't matter since we've only got one thing in our circuit. But let's go ahead and connect to that. And then I'll get one of these ones. The colors for your kit are probably different than what I've got, but the same things will apply. So I'll just connect that there, and you want to make sure that you never connect the positive and the negative on your battery, because that would just create a short circuit across the battery terminals, and it'll just start running away with the current. A lot of current will flow, and then it will just heat up and maybe eventually leak or explode. So careful not to do that. Alright, so now I've got the negative line on my battery going in here, coming over to this part of the resistor, and then the positive line here. So positive through the resistor to negative back to the battery. And we can check now, we've got it on voltage. So if you just place your probes across the resistor, so the same way we used to measure the resistance, and just place it right like that, and see what the value is. So we've got 8.5 volts. It's going to be just a little bit lower than when no voltage or no load was applied across the battery. Now that there's a little bit of current drawing, it's not actually able to supply as much current. But you do see that the full voltage is across the resistor. And if we change this out now, we could put in the other resistor. So let's just try that. And again, we should see the same sort of load across it because it's the full voltage of the battery. So we apply that, and again, we've got around 8.6 volts like we saw before. Now let's try something different. Let's leave that resistor in place, and I'm going to take the other one and put it one end in the same row as the 5.1 resistor, and then put the other one farther up. So now we've got two resistors in series. And we can take this other wire again now and apply that voltage. So now the whole voltage is being applied across both resistors. Alright, so I'm going to just draw a simple circuit diagram real quick for this, and you can do the same if you would like. So we've got our battery, and then this is nominally 9 volts. It's not exactly. Let's just double check again what that full voltage was. So we have 8.61 volts. So let me just scratch that out. We've got 8.61, That's not easy to see. Okay, 8.61 volts. And then we've got two resistors in series. So we've got the first resistor here, and then there, the node in the middle, and then our other resistor, and those are connected across. Again, I'm just going to pull these out real quick, and we can check the resistance so that we know the exact resistance on these. And we've got 5.71 kilo ohms. So 5.71 kilo ohms, and then just check the other one. And I guess I didn't mention it, but the reason you pull it out, if you don't pull it out, then you're measuring sort of the resistance within the whole circuit, which will not give you an accurate reading, so you actually have to disconnect it from the circuit. And it's okay now if I want to measure here, because no current is going to be flowing and nothing else is connected. So now we see 463.2 ohms. 463.2, and your values are probably going to be different because your resistors will vary differently than what mine were. Alright, so let me put that back into the circuit now, and let's check the voltage again. So from here to here, across the 5.1 kilo ohm resistor, that was resistance. Okay, I gotta switch it back to voltage, so again, those are things you want to remember. Don't forget that. It's easy to forget. Okay, 7.89 volts. So let me just record that. So from here to here is 7.89 volts. And then we'll measure across the other resistor. So you just put those in there and hold that there. And we've got 0.721 volts. And this is an example where you could use the hold button. So I'm just going to press the hold, and now I can remove the probes and it'll stay there. So now from here to here, we've got 0.721 volts. Both of those are volts. Alright, now the thing you want to notice here is the ratio between these two. So we've got more of the voltage across the higher resistance one and less across the other. And when you study Ohm's law later in the semester, you'll understand why. But just for now, this kind of a setup is called a voltage divider. And the reason it's called that is just because it divides the voltage in two. And this will be important when we look at our next thing, which is the potentiometer. So real quick, let's just double check the math on this. So if we take our 7.89 volts and divide by 8.61 volts, the value for that we can calculate. 7.89 divided by 8.61 gives us 0.916, and we can check the same ratio now if we look at the resistor values. So it's going to be equal to the ratio between this resistor over the whole resistance. Okay, I'm sorry, the calculation I just did was off the screen, so I'm just going to do that again. So the value we've got here, we're looking at the ratio of the resistors. We're going to have the top resistance there, which is actually 5,710 ohms, and then divide that by the total resistance from here to here. So that would be 463.2 plus 5,710. And if we multiply, or rather if we calculate that, 5,710 divided by 463.2 plus 5,710, and that comes out to be 0.925. So as you can see, that's pretty much the same ratio, and ideally it would come out the same. Due to measurement error, it's probably not going to be exactly the same. But basically what a voltage divider does, you can see that depending on the ratio of these two resistors, you end up with a fraction of the voltage that you apply across that. And so depending on which voltage you want to measure, so you could measure across this one and you would get a smaller portion of that number, or you could measure across the larger one and you would get a larger portion of that. But it's an easy way to take a full voltage and then divide it down to a smaller number depending on what kind of output you want. The current is still going to be dependent on these resistors, but if you don't care about what the current is, A voltage divider is an easy way to step down your voltage from a high voltage to a low voltage. And that's what we're going to look at next with the potentiometer. The next item is the potentiometer. And the one I have here is this little blue box with a knob on top and 3 pins on the bottom. So what this thing is an adjustable resistor. And it's going to be sort of like the resistors in series that we had from before, except that the resistance in the middle is going to be adjustable. So let me just draw this real quick and we can look at it and see what it looks like inside. So we've got this base here, and then the knob on top, and then pins 1, 2, and 3. Now the resistance across pins 1 and 3 is going to be a fixed resistance. So let me draw pin 1 and 3 here, and then in between those it's going to be one resistor where we've got, in this case, 1 kilo ohm. This is a 1 kilo ohm potentiometer. Now the resistance in the middle, so we've also got this other pin, so pin 1 and 3, but we've also got pin 2. And this is going to be like having 2 resistors in series, where the resistance of these 2 is going to add up to the total of 1 kilo ohm. So as we twist this knob, we're going to see more and less of the resistance across, say, 1 to 2 and then 2 to 3. And if we twisted it to the extreme, like let's say we twisted it all the way here to the left, then we can have pins 1, 2, and 3. And now all of the resistance is going to be between pins 2 and 3, and none of it is going to be between 1 and 2. This is just going to be like a wire between them. So now case 2 would be if we twist it all the way the other way. So if I twist it clockwise, now we've got all the resistance between pins 1 and 2, and none of the resistance between 2 and 3. So this would be the full 1 kilo ohm, and this would be 1 kilo ohm. This would be 0 ohms, and this would be 0 ohms. Now that you understand how this works inside, I can show you the circuit symbol for a potentiometer. And that's going to be something like this, where we'll just have a resistor like we had before, and then instead of just having these 2 pins, where we would have, the 2 ends there, we're going to have this third one in the middle. So this would be 1, 2, and 3. And we draw it like this because it's going to be pointing to somewhere in the middle of this resistance. And then the adjustable part of it is that, this can shift from one side to the other so that all the resistance is, between pins 2 and 3, and none of it's between 1 and 2, or like case 2, all of it is between 1 and 2, and none of it is between 2 and 3. So this one here, pin 2, adjusts between points 1 and 3. So we can add this now to our list of circuit symbols. And again, we've got just the resistor portion of it, and then the point in the middle where it adjusts between the top and the bottom. Now, let's just look at this in the circuit so that we can test what we just talked about. If you put 3 wires like this, where they all go to separate rows, then we can plug the potentiometer in so that each pin goes into a separate row. So now if we check the resistance, we can set our multimeter to measuring resistance. And let's just check the resistance across pins 1 and 3. So if we look at that right now, we're seeing the entire resistance, about 1 kilo ohm. And then we can check to see what the resistance is between, say, pins 1 and 2. So right now we're seeing the full resistance across pins 1 and 2, which would mean we should see about 0 resistance across pins 2 and 3. And like we would expect, we've got very low resistance, or almost 0, for pins 2 and 3. Now, if we turn the knob all the way to the other side, now we should see all the resistance across pins 2 and 3, and none of the resistance across pins 1 and 2. And that's pretty much exactly what we're seeing. There's a little bit of resistance in there, but it's very close to 0. And if we just watch that, I'm going to keep these probes on here, as we turn the knob, now we have more of the resistance getting to this side, and I can keep going, and when it reaches all the way to the other side, now we have the full 1 kilo ohm between pins 1 and 2. Now, like I said, this is very similar to the series resistors that we had from before. The only difference is that now we can adjust the point in between. So now, instead of just having it fixed between these two resistor values, we can adjust it from pin 1 to all the way to pin 3, so that this resistance in the middle is going to be dependent on how far we've turned the knob. So let's just remove these two resistors, and then we can place this potentiometer just like we had the two resistors, so that we can have our resistance in between the power and the ground rails. So we want these wires here so that we have our ground or our negative line coming in here on this row, and then skip a row. Oops, I have it too close, too far away. And then we have this one here, so we skip a row, negative, skip a row, and then positive. So we can stick this in, and now we have the full voltage being applied across pins 1 and 3 on the potentiometer. And I'll just plug this back in so we have our battery supplying power to the circuit. Now I'm just going to move these 3 wires over here so that we can measure the voltages. Okay, so now we can use the multimeter and set that to voltage. And I'm just going to check. We can see what the voltage is across all 3, which is going to be the battery voltage. So we've got right now 8.57, 8.56 volts. And if we check now, we should see 0 volts across pins 2 and 3. And if we check pins 1 and 2, now we should see the full voltage, 8.56. And if I just hold these on here right now, I can turn the knob and we'll see that the voltage changes so that right now it's got the full voltage. But as I start to adjust it, we can bring it down until it's reached 0. And now if we were to check across pins 2 and 3, now we see that the full voltage across pins 2 and 3 and 0 volts is across pins 1 and 2. The last components we're going to look at are the LEDs. And an LED stands for light emitting diode. So a diode is a device that you apply a certain amount of voltage to, and then it allows current to flow through it. So it turns on, it allows current to flow. An LED is a diode that when you reach that voltage and the current begins flowing, it also produces light in the process. So the color of the LED is going to depend on the materials inside the LED that make it work. So if you look closely at an LED, you'll see that the 2 leads are not the same length. So let me just hold it like that, and you can see one lead is longer. So the long lead is the positive lead, and the short lead is the negative lead. You can also tell which is which if you feel on the side, or you look here. You're not really able to see this on the camera, but if you feel on an LED, right here on the edge, one side of it is flat, and the flat side is on the negative side as well. So long lead is positive, short lead is negative, and the flat side is also negative. Also in the case of these clear LEDs, you can see inside them, and the larger metal side, it looks like a little metal triangle, that one is also on the negative side. So make sure you put it in the correct orientation. If you don't, it's not going to turn on. It's not going to hurt anything unless you apply a really big voltage to it, but it won't turn on if you don't put it in the correct polarity. The circuit symbol for a diode is going to look something like this, where we have a straight line, and then a triangle, and then the lines coming back out of it. So this would be a general diode, just any diode. If you want an LED, then you just have to draw some squiggly lines coming off of it with arrows indicating that light is being produced by it. In any diode, the direction that current will flow is in the direction of this triangle, or you could think of it as an arrow. So in that case, since current flows from positive to negative, then this side would be positive and that side would be negative. So the negative side is going to be the side that has this flat line on it, and the arrow or the triangle is going to point in the direction that current will flow. So positive side on this side and negative on that side. Now let's try to build an LED circuit. So first of all, let's just remove the potentiometer for right now, and we'll pull those wires out, and let's move the positive one from the battery up here so that we have a little more room to work with. So whenever you have an LED in a circuit, you always want to have a resistor in series with it. And the reason for that is if you don't, then too much current can flow through the LED and burn it out. If you exceed like 20 milliamps, that's normally a good rule of thumb for an LED. If you exceed 20 milliamps, then the LED will get really bright and then burn out and it won't work anymore. So you just want to choose your resistor so that the appropriate voltage that you're applying across both of them with the LED is then going to be okay. It won't flow too much current through it, and then it keeps it within that 20 milliamp range and you'll be fine. So if we look at this LED, we've got the long lead. We want that one on the positive side of our circuit. So I'm just going to put that one maybe right here. And then let's grab our resistor. Let's start with the 5.1 kilo ohm resistor. And I'll just put that in the same row as the LED. And then pull this other end down and plug it in to the negative line from our battery. And it looks like that was maybe a little too far to go. Doesn't quite reach. So I'm just going to move this down so that we have our battery connected to the LED, and then the resistor can reach from the bottom of the battery up to the LED. Alright, so right now the LED is on, and you can try this, and right now it's kind of dim, but you'll find that the current that flows through an LED is what's going to determine the brightness. So this is a large resistance, 5.1 kilo ohms, and now if I swap that out for this 470 ohm resistor that we were using before, the resistance is going to be less, so the current should be more. And we can check this now. If we put that in and swap it out for the other resistor, now you can see the light is a lot brighter. So again, just for comparison, I'm going to put one end of the 5.1 kilo ohm resistor in, and then if I pull this one out and put this one in, you can see it's much dimmer than when I just had the 470 ohm resistor. So the 470 is a lower resistance, it gives a much higher current and a brighter LED. Let's set the 5.1 kilo ohm resistor to the side for the moment and set our multimeter to measure voltage. And now if we check our voltage across the LED, we'll find that it has about 2.05 volts. Now let's grab some alligator clip wires, and if we attach those in our circuit, we can measure the current going through the LED. So I'm just going to pull out the resistor wire here and put it in this other row, and I'll do the same with the LED. So now we've got a break in our circuit, and this is where we can attach our multimeter to measure the current. So just take one of your cables and clip that on the side of your LED, so that's on the negative side of the LED. And I'm just going to grab another wire here. I could just clip it to the resistor, but I want to be able to swap out the resistors and see how the current changes. So I'm just going to plug that in there and leave it sticking up. So now I can clip the other alligator wire to that. Now unfortunately, as I mentioned earlier, I can't measure current with this one anymore, at least the low amounts of current. So I'm going to have to set that one to the side and grab my other multimeter for this part. So we'll just take the negative lead from our multimeter and plug that one, or rather connect that one to this wire coming in from the resistor, and then connect the red one, the positive lead, to the other alligator wire, and we'll just set that to the side there. Now if we set the multimeter to measuring current, we can see that we have a current now of 13.65 milliamps. So that is within our 20 milliamp limit, and you see that the LED is on. Now, if we swap this out, so let me just push hold right now, and we'll save that value, 13.67 milliamps. So I'll just take that one out and then put this other one back in, and we can see what the new value for the resistance is. So again, right now we have 13.67 milliamps, and if I press hold again, it's going to go back to the live value, and we can compare that to what it is with the larger resistance. So now we only have about 1.3 milliamps, which is much less, and you can see that it's very dim compared to what we had when we used the 470 ohm resistor. So again, if I swap this out, you see that we've got 1.31 milliamps, and I can put this one in now. The LED is now much brighter, and again we have 13.6566 milliamps. So clearly the amount of current that we have flowing through our LED is going to determine how bright it is, and that resistance is determined by how large of a resistor we have in series with the LED. The last thing I want to do is combine everything that we've talked about so far into one circuit, and this will actually be a circuit that you'll use for several labs during this semester. So let's start by disconnecting everything that we've got right now. I'll remove the multimeter and the wires that I have for that, and set that to the side for the moment. Now let's take out our LED and the resistor. Pretty much we're going to start from scratch and build our circuit from the ground up. So we'll start here by just building the potentiometer circuit again. So put these two wires in so that you can have your power and ground lines. And then we're going to attach other wires here so that we have, again, the negative line or ground line, and then the middle line from our potentiometer. Okay, so just put those ones in there, and then you can plug the potentiometer back in so that you have the, say, the left pin here connected to these yellow wires, and then the middle pin connected to this orange wire, and the far right pin connected to that orange wire. So we have the positive voltage coming in here and going through to this side, and then the negative voltage coming to the negative line, going through the potentiometer and coming out here on this negative one. Now let's just grab some other wires and stretch that over here. So I'm going to plug this into the same row as we have for the orange wire and move that one up here somewhere. And do the same thing here, so I'll stretch that over to here. And now what we're going to do is use this as our control voltage, our adjustable voltage to control the LEDs. So grab the 470 ohm resistor and just put that one in here so that we have that's connected then to this red wire for me. It'll probably be a different color for you. Just plug that in there and then take your LED and attach that so that it goes from the resistor back over here to this line. And now, as we adjust the knob, we can control the voltage on our LED, which then also adjusts the brightness. Now, I did say earlier that the current is what controls the brightness of our LED, and that is still true in this case. I'm just adjusting how much voltage gets applied between this resistor and the LED, and the voltage on the LED is going to be somewhat constant, like it's going to just use a certain amount of voltage if it has that available. The remaining voltage is then going to be across our resistor, and so the resistor then is going to determine how much current flows. So by adjusting the voltage here, we actually are adjusting the current, which then controls the brightness of our LED. And if you want, we can also try swapping out. I used the red LED there, but we can use the other colors too. So let's just put in this blue one. So now we've got a blue light. And again, we can control brightness with that. So I can swap that out maybe and put in the green one. Now we've got a green LED in here. And I can turn that down too and just get some different brightnesses from that. And it does look a lot brighter on the camera, but in real life it's not going to look quite that bright. you can actually see the color instead of it just being really white. Okay, so I'm just going to put this red one back in for the moment. And now let's check our voltage and current across the LED as we change it. So again, let's use our alligator wires, and I'm just going to clip this to the end of the resistor. That's also connected to the end of the LED. And then I'm going to clip the other end to the side of the LED, and we can see now that we've got 2.044 volts. So now let's just watch that voltage as I adjust it up and down. So you can see that it's being applied. We've got a very low voltage, and then as we increase it, we're getting more. That went from one range to the other. That's why it looked like really large values. So now we've got it going up. We got 1 volt, 1.5 volts. Let's get it up. We got 2 volts. And so you see it changes as we do that. Now we can also check to see how the current changes as we do that. So I'm just going to unplug the LED and plug it in over here. So now we've made a break in our circuit. I'm going to set this to current and then put the red one on the resistor again and the black one on there. So now we've got our circuit that flows through the resistor, through our multimeter, and then back around through the LED to the potentiometer. So we see right now we've got 13.3 milliamps, and as I adjust this down, you'll see that the current does drop as we adjust the voltage, just like we said. And if we bring it down all the way down to 0, it does turn off. It turns off before that, so we can turn it up a little bit. We have no current flowing right now, or a little bit. So right now, this is not turned all the way down, but we do have 0 current, or at least less than this is able to tell. So as I turn that up, now you can see that it turned on, and then as we increase the current, or increase the voltage, then the brightness does increase. Okay, let's take this multimeter back out and put the circuit back the way it was. So I'm just going to plug the LED back into the holes there, so that we have the LED on and just controlled by the potentiometer. The last thing I want to do is practice drawing the circuit diagram for the circuit that we just constructed. So let's always start off with the power source. So we've got our battery here, where that's the positive and that is the negative. And this is our 9-volt battery. I'm just going to put it as 9 volts right now. I know that it's a little less than 9 volts at the moment, but we're just going to put 9 volts right now. And then we'll draw that up and coming over. So those are going to be the 2 lines that we have, the black and the red, coming from our battery, and then going through, the black becomes this yellow one here, and the red becomes the orange one right here. So then we've got our potentiometer in the middle, so that would be like that, and then we've got the other 3rd wire coming off of it. So this is our potentiometer right here, and that is a 1 kiloohm. Then we didn't connect anything else to this top one. That is the 3rd wire, so we didn't have anything coming out here. But we have ones coming out from this pin and that pin. So that would be here and here. Now this bottom one, we have that coming over and connecting to the LED. So we'll have that come up, and then we've got our LED. And let's draw the little squiggly lines so that we can designate that it's an LED and not just a regular diode. And then coming over from this pin, that's the orange one, going through this red wire, so that's coming across here. Then we go through this resistor, so let's draw the resistor. And then this connects again to the LED. And that's our complete circuit diagram. We can mark the resistance of that, so that one is a 470 ohm resistor. That's our 1 kiloohm potentiometer, our 9-volt battery, and the LED. So this is really all there is to it. When you build a circuit on a breadboard, you just figure out, the rows are connected, the power rails are connected, and then you just plug your components in and then connect wires between the components so that it completes the circuit. And then when you're drawing your circuit diagram, you can just have your power source, you just have all of these components, and then you just draw the lines that connect them just like the wires do on the breadboard. And I know some of these are like diagonal. Normally when we draw circuit diagrams, we want to keep nice horizontal lines, but it's still the same layout, even though this diagram looks slightly different than this. It is good to try to draw your diagram and build your circuit similar to each other. So we do have our battery off here to the side, and then we have the potentiometer going to the right, and then we have the resistor, and then the LED off here to the side. So if you're able to draw it here in the same sort of orientation so that things, are progressing maybe left to right, or at least, this one was going horizontal, this one's going vertical, so I drew that the same way on my circuit diagram. So as long as you do something like this, where your circuit diagram reflects the breadboard or the breadboard reflects the circuit diagram, it's an easy way to troubleshoot. You can see that this looks like that or that looks like this. So just do something like that when you're building your circuits or drawing your diagrams so that they all match and it's easy to see what's happening in each one. And that's it for this introduction. Hopefully this will help you as you progress through the semester and build the circuits to do the labs. I know that sometimes building circuits on the breadboard can be daunting if you don't know how to do it or you haven't had a lot of experience with it. So hopefully this will help minimize the problems that you have so that you can focus on the experiments and maximize your learning this semester.